Hi everyone, Brandon John here at Engineer Essentials. Today we're going to talk about why use profile over coordinate dimensioning. We've shared in all of our webinars, also in our training classes, that we here at Engineer Essentials are not GD&T evangelists. So what is a GD&T evangelist? This is a person who seeks to convert others to the GD&T faith, especially by public preaching. We made that up, of course, but what we mean is we're not pushers or hardcore users of GD&T. We're not trying to get everybody to use GD&T 100% of the time. We're realists. We understand that not all of you can. Doesn't work best for all companies. But we did want to show you why profile tolerancing does have a benefit over coordinate dimensioning for locating not just our features of size, that one I think is a given, but for locating surfaces. Okay, so first I want to show you, like we always try to do in our webinars and these little videos that we make, the rules from the standard, or at least recommendations. It's not always rules. Sometimes it's just recommendations. So up here at the top, ASME preferred method for dimensioning tolerancing a surface feature. So on page 186 out of the Y14.5 2009 standard, what I have labeled up here, or what I've stated up here, this is probably one of the biggest, boldest, most ignored statements in the Y14.5 2009 standard. Personally, I think it goes unread by many. It took me a long time to even catch it myself. So it is A.4.1, paragraph 2.1.1. States in there in paragraph 2.1.1 has been revised to emphasize or encourage the use of basic dimensions and geometric tolerancing as the preferred method for controlling the form, the orientation, and the location of features. So the use of direct tolerancing methods, limit dimensioning, and plus-minus tolerancing should be used to control the size of features only. So what does this mean? Simply put, this means that you should use position tolerancing for controlling features of size. That's what we teach. And then profile of a surface for locating and orienting all surface features. Remember that profile of a surface will always control form. In our course, we teach that a profile can control all of SLOF, meaning size, location, orientation, and form. But what they're pointing out here specifically is for these surfaces, use profile of a surface. Now, again, what they put there in the paragraph up top, 2.1.1, is that they're trying to emphasize. What they've listed in 2.1.1 is that they're trying to emphasize or encourage the use of basic dimensions. It's not that it's mandatory, but when they put something like this in the standard, they are trying to prepare everybody for something that's going to come in the future. So when we go to the 2018 standard, that's where we see where they stop to support these plus or minus tolerancing altogether for the location of surfaces. So down at the bottom there, according to ASME, the use of plus or minus tolerancing on dimensions to locate features of size and surface features should be eliminated or avoided as a best practice. Okay, let's take a look at this example drawing. On this one, I have coordinate dimensioning applied, and we're going to focus in on the window here in the center of this part. So this one here. Now, I'm going to highlight these in red, but on this window, it's the only feature that we're going to look at for this example. There are other details on this drawing that we could address with this approach as well, but just going to look at this window here. In our course, we have the GD&T Basics framework, and there's 4 elements that make this up. It is size, location, orientation, and form. So we're going to walk through this coordinate dimension print and look at each one of these elements and just see how it's controlled. First up here is the size. On that GD&T basics framework with size, location, orientation, and form, the reason why that's so important is that's how we dimension prints. That's how we know that we have obtained our goal there for creating that drawing. Every feature of size must meet all of SLOF. It must have size, it must have location, must have orientation, and must have form. Now, when it comes to surfaces, it's not going to be size on all those surfaces, not to say that we can't use profile to control that, but as was stated back there by ASME, it's really the location and orientation that they would like for us to use profile tolerance for these surfaces. Okay, on this one here, we have the size I've highlighted. So what controls the size on this? And again, we're looking at that window there in the middle of the part. So here we see we have these two vertical walls here. We have a size on that, and that's 2.5 inches plus or minus 5 thousandths. So that's one of the sizes. The next one is the actual vertical space on here. I call this direction Y and the previous one X. So on this one, we have a 2.25 inch dimension plus or minus 5 thousandths. And then last on here, for the size anyway, for this window, are the radii. So the radius dimension that's on the print, it's 4 times, right? That signifies that it is a pattern of 4. But 4 times, and we have a radius value here of 1/4 inch, plus or minus 5 thousandths. And wanted to point out here real quick that a radius is not considered by the ASME standard a feature of size. When we're doing coordinate dimensioning, it does still have a plus or minus tolerance on that. Now, these are easily converted into profile of a surface, but not done on this one here. Obviously, the rest of the shape is plus or minus tolerance and treated like feature of size. The reason that I wanted to point that out, though, is when we get into converting over into GD&T, see it very often, but we can't put a position tolerance on the radius. So that is forbidden according to ASME. Can't put position tolerances on those. Another thing to point out here is I have the form listed up there at the top, so I wanted to just a reminder on there that with these size dimensions, due to rule number 1, form is controlled. So on those flat surfaces going around this window, we don't have to worry about applying flatness in there unless there was some reason that we needed to refine it. But it is controlled by the 2.5 and 2.25 inch dimensions. So that also is taking care of parallelism between the two surfaces to a degree. Now, they do state rule number 1 does not control the orientation, but we do have envelope requirements for these, both the 2.5 and the 2.25. So we have envelope requirements, and even though there's no rule for the 2.25 and 2.5 to be oriented to each other, the two surfaces do have to lie within the MMC and LMC limits and ultimately that envelope. Okay, next up is location. So the previous slide we talked about the size. We talked about how size is controlling form. So from SLOF, we've got the S and the F. We still have L and O to talk about here. So this one is location, which is the L. So what controls the location of this window? Remember, we're still talking about the window here. So on this surface here, this dimension is coming from the datum feature. So over on the right-hand side, we see that there's a 7/8 dimension on there coming from the datum feature. And then the next one up here on the side, we have this 3 3/4 dimension coming from datum feature C. Okay, I wanted to point out here that I stated that these are located from the datum features. This is important because these are not coming from datums. They're coming from datum features. This changes the requirement for how it's to be inspected. And I know a lot of you out there watching this video, for that 3 3/4 dimension there, you might turn this up, put it on a granite table, and sitting on datum feature C, and then come up, let's say, with a height gauge and take some points across that surface. Well, according to ASME, you have to measure from the datum feature, which that would mean these are 2-point measurements, meaning that you can't come from the granite table. The granite table is going to serve as a datum simulator, and that would mean that you're measuring from a datum. We can't do that. We have to come from the actual datum feature, meaning the actual surface on the part. Just where those arrows are showing right now, we're going to take dimensions from there across calipers, micrometers, whatever your method is. But we do not want to simulate a datum on that left side there, datum feature C, nor do we want to do that on B. All right, last but not least is the orientation. So at this point we have size, form, and location taken care of. So the last one here is the orientation. And when it comes to coordinate dimensioning, oftentimes you will see angles called out, plus or minus tolerancing. But on this particular print for the window, there's no angles called out on there. It looks to be 90 degrees from, let's say, datum feature B. It also appears to be parallel to datum feature C, but there is no parallelism or perpendicularity geometric controls called out on the print. And because there are no angular tolerances on there, we have to go to the title block. So down here in the title block, this is typical for most drawings anyway, to have some sort of angular control down there. And this will be when nothing else is specified, and this is what they state here. So if you move over here and take a look at this, this is the tolerance block in the title block. Unspecified tolerances, angles are going to be plus or minus 1 degree. So that is going to apply to every surface on here unless stated otherwise. So whenever we're not using geometric controls and we're relying on these coordinate dimensions and tolerances, we do go to this, we find that tolerance, and we will apply that. So we'll zoom in and take a look at this here. So these are the two surfaces that we're looking at. And the reason that it's these, the dimensions are going to these two surfaces. So we want to start with those. Now the angular tolerance applies, like I said, to every surface. So looking at this is where our intersection is. Now you might wonder, why am I not starting at the top of the radius? So look at where I've thrown the tolerance zone down here. It's down there at that surface that's located 7/8 from the datum feature. Again, not the datum. The reason that I've done this, and if you go into Y14.5, there's a conflict here. I call it an argument, but there's a conflict here of where does the angular tolerance zone start? Does it start at the tangency of this fillet, the radius, or does it start down here where the dimensions intersect? This is open a little bit to interpretation, and that's one of the reasons I don't like this method. But if you read in the standard, the radius, each one of them, the radii, do not have center marks with dimensions going to them. This means that what we call it in the engineering world or the CAD world is that these are corner treatments, and they aren't the, if you will, the primary features. The primary features are the four walls, and that's why the dimensions are going to the intersections. The dimensions are not going to the fillets. If it was going to the fillets on this drawing, I would have changed my start point for the angle to be at the tangency of the arc, because then we have a location for the specific radius. And we've already covered location, but it would have a location on there for the radius. And then we would know that wherever that feature of size or the size of the radius comes in at, we would start the angle from there. So to keep it simple, we're going to do a video on that later on, talking about these radius and how to tolerance it, how to locate it. But to keep this one simple, I just threw it down there in the corner. Now, do notice over here that there's a space from here to here. Now, the reason that it's that way is because right here in this note, I put note where the tolerance zone starts and ends, side to side. The location allows the vertex to be anywhere from 3.725 to 3.775, because that was that 3 3/4 dimension plus or minus 25 thousandths. So the actual start point is able to slide, adjust side to side, based off of wherever the actual dimension comes in on the manufacturer component. One thing that I do want to point out, this doesn't change the angle or cause the angle to grow. No matter what, down there in the title block, it says plus or minus 1 degree, so we only get a total of 2 degrees tolerance on that. This is going to orient that surface. Now, it is an orientation from the datum feature, not from the datum. And like I said, this would be for all of our surfaces on here that we would apply this angular tolerance to. If you're like me, I've had to inspect angles my whole career. I much rather inspect either angularity or even better, profile the surface. Much easier for me to inspect because I don't have to deal with angles at all. But with this type of tolerance called out, you do have to deal with angles. You have to measure that angle to see whether or not the surface came in. This means for a lot of you out there that are machinists, you're going to have to do a little bit of trick here and find out where your values can be whenever you go in to take your dimensions, because you're probably not going to actually inspect the angle. You're going to mathematically figure out where that angle is. Okay, so here I've taken the same drawing. I've removed the coordinate dimensions for the window, and I've applied basic dimensions and a profile tolerance, profile of a surface to be exact. So let's walk through this the same way we did the coordinate dimension print, and we're going to look at sloth. Okay, so the first one, what controls the size? Well, we have the profile tolerance up there in the feature control frame, and because it has the all-around symbol there, we're now controlling size. And I'm only covering this one first because of out of sloth, S comes first, so we typically would look at this in other ways, but for the sake of this, we're looking at size first. So that all-around symbol locks that shape together. So that means the top surface, the bottom, the two sides, and all the fillets, it locks it together as like a pattern of one. So we have different shapes on there, but it turns it into a pattern of one. And we look at it like the overall shape now. And we're going to define it with basic dimensions. So 2.5, remember we had plus or minus tolerancing on there before, and then 2 1/4. And again, they're basic. So the fillets, we've made those basic. And then here's our tolerance zone. And I have it kind of exaggerated here just to make sure that you could see it. But this is our tolerance zone. And because it has the all around and it's fully defined with basic dimensions, we have a single loop, if you will. It is truly it's what we call the true profile that this is distributed from. So any single element on any surface going all around this, because it's a 5 thousandths profile tolerance, and that's arguable whether or not that's the appropriate tolerance. The design is going to require that. But according to the way that it is right now, any given element on the surface could either move in or out by 2.5 thousandths, a total of 5 thousandths. Oftentimes we do treat profile tolerancing like plus or minus, because we have an exact location where it's supposed to be, and then from there it can deviate half of the tolerance in, half of the tolerance out. Okay, so next is the location. So we have the 3 3/4. Remember that one before, locating the coordinate. but now it's converted to basic. And now this is not coming from a datum feature anymore. That's important to point out. This is coming from datums. The 7/8 over here, the 0.875, that one's coming from B. The 3 3/4, that one's coming from C. But they're coming from datums now, and they're locating the tolerance zones. Very important to understand with GD&T, it's all about tolerance zones. So we didn't have all of these tolerance zones with coordinate dimensioning that were all tied together and locked together, but they are now. And whether you know this or not, this makes it more simple. Oftentimes, people will tell me, or anybody else at our company, that profile tolerancing complicates things. It makes it more complicated. And that's not true. When it gets complicated is when you have complicated geometry. But on this right here, this is very simple. Nothing complex about this. We can definitely manually measure this. And what I mean is we can now put this on a granite table. Once we have all of our information here, we know what the requirements are. It's easy to put this on a granite table and use a height gauge, whether it be a flat blade or you have a dial indicator stuck on the end of it. You're obviously going to have to calibrate that and zero it out. But once you do all of that, it's easy to take these measurements. Okay, so the next one is the orientation. So this is critical too. This is very important in GD&T to understand. Not only what I said a while ago, that the profile of a surface tolerance here that's the tolerance zone. And then we have datums to the right of that. Our datum references, in this case, it's ABC. So with the primary datum, what it's going to do is take the tolerance zone, which we can see here in red. It's going to take that tolerance zone and it's going to orient it to A. Well, if we move over to the right side over here, we see datum feature symbol A over here. We know that this is the datum feature, and we know that the datum will become tangent to that, which for us, the datum simulator, will say is going to be a granite table. But whatever it's going to be, the simulator doesn't matter. It's going to take that tolerance zone and orient the tolerance zone to that datum first, so to the primary datum. Now, if this primary datum could locate it, it will, but in this case, it cannot. Orientation is the only thing established here. But that's something I always try to point out to the students right away, is that first datum is going to orient a tolerance zone. And then if it can locate it, it will. If it cannot, we'll move to the next one. So when we go to B, going back up to the feature control frame here, the question is, can B also orient the tolerance zone? And the answer is yes. Because if we took it and made it perpendicular to A, it could spin around and go anywhere. But B is going to come back in and establish parallelism or perpendicularity, whichever one you want to call it. But it's going to orient this tolerance zone to B, to this surface down here. And it's truly the datum now that we're orienting to. We're not orienting to the datum feature. So now we have parallelism set for B of the tolerance zone. And then, like I said before, if it can handle, or if it can do a location control also, it will. And in this case, like we said, it does. The 7/8 over here is going to locate that from B. Now, side to side still open, right? We've covered orientation to A, perpendicularity. We've covered orientation to B, which is a parallelism or perpendicularity, take your pick. And then a location from B. Well, now we're oriented to B, which means that it's automatically perpendicular to C, right? And again, or parallel, take your pick. But it's not located yet from C. So looking at the 3 3/4 dimension again, now this is going to come in and locate the tolerance zone from C. And what it's doing is locating true profile, and the tolerance zone is distributed from there. So now we have a tolerance zone that is perfectly oriented and perfectly located from the datum reference frame through basic dimensions. So we're ready to take the measurement. Now, like I said, this now becomes a very simple measurement because we have datums. So up here in the datum reference frame, in the feature control frame, to be more specific, we have these datum references up here, and it tells us how to set the part up and how to take the measurements, and also that we are coming from datums now. So this does mean we can simply stand this up on its side on a granite table. Now we would want to use something else like a 90-degree plate to put A up against. That way we know that the first requirement is that A is locked down. Remember, 6 degrees of freedom. So it would go up against the 90-degree plate. That is also a datum simulator, just like the granite table. We would secure it up against there and then slide down to the granite table for B, because it's a secondary. And then if we needed to, slide it over to something to stop C. But this is going to lock the part down. Now we can take a height gauge and come in and just simply see, when we touch off on the surface, is it where it's supposed to be? Now remember, in coordinate dimensioning, you're not allowed to do that. Those are measurements coming from the datum feature, from the surface itself up to the other surface. But when we have profile the surface, and we have this full datum reference frame, everything's defined with basic dimensions, it's very simple. So you always have to ask yourself, when you're doing these drawings and you think that you're making life more simple for everybody by leaving it in coordinate dimensions, is it really doing that? My opinion is no. Now granted, there's always a place for coordinate dimensioning. There's definitely a place for profile tolerancing, but what I have found out over the years is that when you switch over to profile of a surface, you are aligning with the way that we have all been taught to measure, which is take the part, put it on a granite table, grab a height gauge, micro height, whatever it's going to be, and take your measurements. And most of us don't know that we're not allowed to measure it that way when it's coordinate dimensioning. So now switching over to profile of a surface, all it simply does is align the inspection method or process to the print where it didn't match before. So that is the big benefit there. Did want to point out one more thing here. Don't forget, profile always controls form. So what I mean by that, and we have a webinar about this that you can watch, but what I mean by that is up here, whether we have a single datum, no datums, 2 datums, or in this case, 3 datums in that reference, no matter what, it is going to control profile. What becomes questionable with these datums is as we start to add them in, now what else are we controlling? We're going to start to control location. We're going to start to control orientation, or both. And it can also incorporate size when we have that all around, or it's across or applied to two opposed surfaces. Now size comes in there too. But just in its easiest state with no datums in there, it does control form as well. So I didn't have that included on the left side, but I wanted to show it real quick just so you know form's always controlled here. So that's all of SLOF. That meets all of the requirements in there. And like I said, it does make it easier to inspect. Okay, well, thank you for joining today, and let us know if you have any questions. Thank you.